Hi guys, this video today is going to cover things on springs. A couple of things. There was a version of this floating around that was missing some pieces, and I don't know how they fell off, but if you have an older version, make sure you have this couple of sentences that was dropped off, and then also number 12 and 13 had dropped off. So if you miss those, I think you can, if you've printed it out, I think you can use that paper copy that you have. Just add these somewhere in the margin or something like that. But let's take a minute to go through here. First of all, reading through what's going on. To determine the period of a mass oscillating on a spring, we use this equation, and then it explains what all the things are. To determine the horizontal location with respect to time, we use this equation and explains what all those things are. Please be sure that your calculator is in radians when you use this equation. This equation is also the same equation that we were using a little bit ago. It is the same equation that we use for a pendulum. I'm going to show you on your AP sheet. So here's your AP sheet. Here is this. This works for both a pendulum and a spring. So you just might make a note on your AP sheet that this is the same equation on each of those. All right, let's go back to the paper. Basically, what's happening here, like if we use these diagrams to talk about, it starts in equilibrium, we can pull it back, and it's going to go back and forth and back and forth and back and forth and back and forth. And as it does that, you might need to know, okay, in 4 seconds, where is it going to be? How far away is it going to be? That's what that equation is going to tell you, is at a specific time, where in its oscillation, where will it be? That's what that equation tells us. Okay, so here's an example. We have an object of mass 4 kilograms oscillating horizontally on a spring with a constant of 200 newtons per meter. Again, that spring constant, that's your K, and that's a lowercase k, and it tells you how stiff or how loose the spring is. And so what is the period of oscillation? Okay, remember T stands for period. And in this case, I don't have a subscript here, but I really should. This should be the T sub S, because the other one we were looking at the other day was T sub P. It was similar, but this time the mass does matter. The mass affects things. And so the more mass you have on there, the slower it's going to be, the longer it's going to take. Okay, let's just go back to where we were. So we're going to use this equation and we're going to plug things into that equation. So I have the period of the spring, and that's what I'm looking for. I'm going to plug into my calculator 2 pi times the square root of the mass, 4 kilograms, over the K, which is the 200 newtons per meter. And now it's just a matter of plugging that into our calculator. So take a second, pause the video, plug that in, and see what you get. All right, on your calculator, you should have gotten 0.889 seconds. Frequency. Remember that frequency is just 1 over the period, or period is 1 over the frequency. So they are reciprocals of each other. So all we have to do on our calculator, if you still have that on your calculator, you know there's this x to the negative 1 button, and that button on your calculator, that button is right here, x to the negative 1. It's on the left-hand side underneath the math button. And so if you have that number on your screen from a second ago, you can just hit that to the negative 1. And I actually did not have it on my calculator, but I just plugged it in. So this version is the kind of the truncated version. And so I'm getting 1.12, or you can take 1 over. And either way, you're going to get 1.12. And remember, when we talk about frequency, that is measured in hertz. So this answer is 1.12, or if you didn't round it, I think it came out to be 1.13 hertz. And the abbreviation for hertz is just Hz. And again, just for your information, a hertz is 1 per second. So this tells you how many per second. That's what that's telling you. This is telling you it takes 0.889 seconds to make an oscillation. This is telling you it will do 1.12 per second. That's what that's saying. A hertz means per second. Okay, let's look at problem number 10. Problem number 10 is asking about if we have this force used to compress a 2 kilogram mass on a spring, 50 centimeters, how much energy is stored in the system? So just to let you know what's going on here, we have this spring, we have a 2 kilogram mass, and this mass, something is pushing this mass so that the mass is pushing against the spring. And it is moving it 50 centimeters or 0.5 meters. How much energy is stored in the system? Well, the formula for spring energy is 1/2 kx squared. And K is that spring constant that tells us how stiff or how loose a spring is. So far, the sentence didn't give us the K. And so we need to come up and figure out what it is. Now, I will mention that a couple of problems ago, they did give us this K over here, but this is a new problem. It's a different spring. It's not the same one. So we're going to have to go back and find what the K value is. And so if you go back to your AP sheet for just a minute, this was the formula we were talking about a second ago. These are the main formulas for period that we need in this unit. And then this is the equation for the spring force. The spring force, F sub S, is equal to K, that's that constant we're talking about, times X, that's the distance. So we are going to use this formula to figure out the K. All right, so we know that the force is 10 newtons. The K we don't know, that's what we are looking for. And the X is 0.5 meters. And so now we just have to do our math and divide this. So I'm going to take 10 divided by 0.5. And so I come up with K is equal to 20 newtons per meter. Newtons per meter is just the unit we use for that constant. All right, now that I have the K, now I'm ready to use this equation. So I'm going to use this equation. I'm going to plug in the numbers that I know. All right, so I plug in my information. Go ahead and put this into your calculator and see what you get. All right, when you plug it into your calculator, you should be getting 2.5 joules. As far as the units go, if we look at our units here, this is going to multiply out to be Newton meters, which is what I have written here. But a Newton meter is a joule. So this is the 2.5 joules that we are looking for. Okay, for the next question, this is going to be the equation we're going to use. Let's talk about what this equation is representing. What this is saying is that the period of oscillation depends on the mass, and it depends on how stiff the spring is. And so the greater the mass, the greater the time, the longer it's going to take. And the greater the K, that is like the more stiff it is, then the less the time it will take. Okay, so we plug in those numbers. We get 2 pi times the square root of 0.1, which comes out to be 1.99 seconds. And actually, for significant digits here, I could probably just say 2.0 seconds for that. Remember, on the AP test, they are not very picky about that, so I'm sure they would take either one of those answers would be fine. So that just tells you how long it would take given that certain mass and that certain constant on the spring. Notice it does not rely on distance. In other words, like if this spring, let's just use this for example, if we pushed it in 0.5 meter, or if we pushed it in 0.75 or 0.25, it does not matter the distance. The distance does not matter on this one. So just like on the other one, where mass didn't matter on pendulums, on this one, distance doesn't matter. It's going to take the same amount of time, which is just an interesting concept. It doesn't seem right, does it? Okay, number 12, that's one that fell off if you had an earlier copy of this. This question, there's no math to do for this question. It is written right here. But you just needed to know what amplitude means. Amplitude means how far it is pressed, or displaced, we could say. So how far it is displaced, that is the amplitude. So we have 50 centimeters, or if we kept it in SI units, we would have 0.5 of a meter. Now we need that because for this next one, it is asking for what's going to happen 3 seconds into the oscillation. And so for number 13, if you look up at the top of your page, this is the equation that we're going to use for number 13, this displacement equation. And again, on your AP sheet, it is here on your AP sheet. This is your displacement equation. So here's my equation. Let's talk about what each of these things mean. And we found the A. And this is the amplitude, that's a capital A. So displacement is what we're looking for. The amplitude is 0.5. We're going to multiply that times the cosine, I guess that should be 0.5 meters, times the cosine of 2 pi times the frequency. Well, we don't know the frequency yet, but we do know the period. And frequency is just 1 over the period. And so that's just going to be 1/2. That's going to be 0.5 hertz. And our time that we're asking for is 3 seconds. So if you do a little bit of simplification here, you see that x is 0.5 times the cosine of 3 pi. This is the one we need to be in radians for. And so make sure your calculator is in radians. The reason we're in radians, this is not degrees, is it? Okay, since it's not degrees, it must be radians, 3 pi radians. Some of you know what the cosine of 3 pi radians is off the top of your head. Some of us don't. So let's go ahead and put that into our calculator and see what we get, and then take half of it because it's 0.5 times that number. Okay, you should have come up with an answer of a negative 0.5. And let's talk a little bit about what that negative means. Okay, what that negative 0.5 means is it means 0.5 meters from the equilibrium point, but on the opposite side of the release. In other words, if I pushed it in 0.5 and then I let it go, then 3 seconds later, it's going to be 0.5 the other direction. It's going to be over here, 0.5. So the negative just means on the other side of the equilibrium, and then the 0.5 meters obviously means that's the distance. Okay, the next question is we have to think through it logically. If the mass were increased, that's typo, if the mass were increased, which of the following values would change? Amplitude, energy, period, frequency, maximum velocity, or minimum velocity? Take a minute right now to think about that and say what you think it's going to be. I'm going to explain it. Let's talk about it. Amplitude is the maximum distance that it goes. I kind of referred to this a second ago, but the mass is not going to change the amplitude. If you look at this, this is the only equation that has amplitude in it, and there is no mass in that equation. So it is not going to change the amplitude. The energy, let's think about energy. Here's our spring energy formula. And on this one, I'm going to go back and double check because on this one, mass does not play into the spring energy formula, but it does play into the kinetic energy formula. That is, the more mass there is, the more energy there is. And spring energy changes into kinetic energy and vice versa. So I'm going to put maybe a question mark on energy. My original thought was no, it doesn't, because it doesn't play in here. But my second thought is, well, what about that mass here? So I think it might play into that. Let's go back and I'll double check that and come back to you. On period. So the period formula is here. Here's our period formula. Does mass affect the period? Yes, it does. Mass does affect the period there. So the mass will definitely affect the period. How about the frequency? Yes, because frequency is 1 over period. So if it affects one, it affects the other. Maximum velocity. Yes, it is going to affect the maximum velocity. Going back to this equation here, I'm going to stick with yes on energy. I think that is going to affect it. Again, I will double check, but I'm pretty sure that's going to be right. The kinetic energy has mass involved. The more mass you have on there, if you watch the videos that I had posted, the more mass you have on there, the slower it's going to go. So that's telling you energy, maybe not. But the more mass you have on there, the slower it's going to go. So it will affect the maximum velocity. What about minimum velocity? No, because at the equilibrium point, you will have a velocity of 0, regardless of the mass. Since we've talked this through, I'm going to go ahead and cross out energy again. Energy is not going to be affected because the mass will change, but what that's going to do is slow down the velocity. So the more mass you have, the less velocity you're going to have. This energy equation is going to stay constant regardless of the mass. This energy equation will change, but both the mass and the velocity will change. And so, no, energy is not going to be affected. If friction were present in the system, which of the following values would change as the system continues to oscillate? And I will try to find some concept builders or something that might have some of that friction in there that you can see. But is it going to change the amplitude? Well, if you think about it, if there's friction involved, the motion might start off like this, let's say, and then it's going to get smaller, right? I mean, the friction is going to make it less and less, so it is going to change the amplitude throughout time. It is also going to change the energy because it's going to slow it down. So slowing it down is going to change the energy. It's also going to affect maximum velocity. because again, that friction is going to slow it down. It's not going to affect minimum velocity because we will always have the place where velocity is equal to zero. You can tell I skipped over period and frequency because originally I had said no, it should not affect the period, and no, it should not affect the frequency. If it's affecting the amplitude this way, notice the way I've drawn it is actually correct. The amplitude is changing, it's getting shorter. I should have drawn a little bit better. The period, though, should not be changing. In other words, this distance, this distance, this distance should all be the same. So it will not affect the period of frequency, but it will affect the amplitude. Okay, again, I will try to find some concept builders that help us to see this, or maybe some simulations that can help us to visualize some of this. But I think also some of this information might also be on some of those GIFs that I shared. Okay, that is it for today's lesson. Like I said, look for in the future a couple of online things that we can do to kind of practice some of this stuff and visualize it a little better.